Okay, good morning and welcome to this morning session. It's a pleasure to have Nima Lashkari here from Purdue University, and he's going to tell us about Emergent ADS2 from intersections of future algebra.
Thank you so very much for the invitation, the opportunity to speak here, and thanks for showing up this early in the morning. So if my handwriting is hard to read, I blame it on my iPad pencil. The tip of it needs to be replaced, and I just haven't had a chance. So I'll try to read all the slides. All right. So today we're going to be, I think, yeah, okay. Is there, let me just zoom a little bit. Yeah. So, okay. These are the references. There are a couple of papers with Keiichiro Furuya, Kuing Leung Lam, Mudassir Musa, and Shoei Youssef at Purdue. Shoei is here. And there are a whole bunch of other references I should mention. Hong Liu and Sam Luthauser, Elliot Gesso Liu, and there's a lot more. But so I already apologize if I will not do justice in terms of references. All right, let's go forward. It's not moving forward. All right, so a little bit of motivation. So I have actually two parts to my motivation. Part of it is a motivation for a physicist, for a holographer, and part of it is motivation from mathematician's perspective. I'll skip the second part because of time. But and if you're interested in knowing about it, I'm happy to tell you guys about it. All right, so the first motivation, the way I want to pitch it, is emergence of space-time in holography. So we've made a lot of progress in the past 2 decades, or past decade. And when we realized that thank you. When we realized that there is a connection between entanglement and emergence of space, started with the celebrated Ryu Takayanagi formula, and then Mark van Ramsdonk made this seminal observation that the connectivity of space-time could be related to entanglement. And there has been a lot of progress since then. We've learned about bulk reconstruction in the language of using entanglement, the quantum error correction structure, holographic tensor network, and all that. Now, for the motivation part of this talk, I want to point out that a lot of these developments focus on reconstructing the bulk geometry on a constant time slice, right? And from the point of view, for example, tensor networks or quantum error correction, time evolution is somewhat obscure. So there has been a lot of work on that direction. I don't want to say that that work is not helping us understand, but it is fair to say that the progress has been mostly on reconstruction of a constant time slice. So the question is, what about the bulk time, right? Is there some sort of sense in which you could talk about tensor networks in time? There's been other suggestions. Entanglement is not enough to construct space-time. Maybe it's complexity, and you could see the connection between space-time and complexity. But we'll not be talking about these aspects today. All right, so today, what are we going to talk about? We're going to talk about something more specific. We're going to be talking about this diagram that I drew it over there as well. Imagine finite temperature states of some holographic theory. This could be SYK, this could be N equal 4 super Yang-Mills, compact finite circle looking at the S wave. I keep drawing this picture because I'll be mostly interested in the S wave, the spherically symmetric part of the story. There are lots and lots of theories here that their finite temperature states is universally described using this geometry, right? This is some sort of an eternal black hole geometry. So they're dual to the same geometry. This geometry has a whole bunch of isometries. For example, it could be if it's eternal black hole, there is a bifurcated killing. There's a killing flow. It could be ADS2 Rindler, at which point, at every point you have ADS2. That will be the topic of the talk for today. Or other things that it has is approximate isometries, right? This is a smooth geometry, so at every point you have the action of a local Poincare group. Algebra, sorry. So where are these on the boundary theory? They should be universally encoded somehow on the boundary theory, these symmetries. This is what we're going to be after. what do these holographic theories have in common that allows for the action of all this large symmetric algebra, right? All of the holographic theories should have this symmetric algebras. Any questions about the motivation? Yeah.
Array structure is just inbuilt into the structure of a manifold, right? So what do you mean by saying they're approximate isometries?
Well, locally flat. When we say locally flat, it means that locally there's a sense in which there are the local Lorentz transformations. Where are these on the boundary? For example, in the SYK, where is it? Good. All right, so I had some discussion from the point of view of math, but I will skip it. I just want to say that you probably have witnessed there's been a lot of work in operator algebras in physics and in our community. And I think part of it has to do with the fact that the operator algebraic perspective gives us some advantages. So I'm more than happy to tell you a little bit more about the high-level motivation for that, but for now, let's skip that. Oh, by the way, one little comment. Every time, because I skipped the math intro, everywhere you see measurable set, think of an open set. If you don't know if it doesn't matter otherwise, right? Because, all right. So let's start by talking about how we think of geometry in a quantum system. So what we often talk about are local quantum systems. These are systems where we have encoded geometry. We have used geometry to define such systems. So here's a prescription you could think of. You start with a manifold M. It could be continuous or discrete. It could be Lorentzian or Riemannian. So Lorentzian are in the parentheses, so you have to go with that. It could have a metric, but in general, all that matters is that it has a measure. So the metric will give you a measure, a volume measure, right? To every such manifold, to every open set of such manifold, you could associate a von Neumann algebra. If I'm very rigorous, I would call it a C-star algebra because I replace the measurable set with the open set, but it doesn't matter. We associate an operator algebra, right? So here are some examples. Here's a bunch of spins that we associate. There's some sort of a graph. We associate qubits to degrees of this. Sometimes we could associate degrees of freedom to edges or faces of some sort of triangulated surface. We'll see how is that different. You could have some sort of a phase space. You associate some algebra of abelian functions on the phase space, or you could have space-time, and then you have to talk about causally complete regions. Is that good? So this is what I would call encoding geometry. So using geometry to define local, quote-unquote, local net of operator algebras. Every time I said net, think of it as a directed sequence. You see, net is just a fancy term in math for generalization of a notion of a sequence, right? So, yeah. You have a bunch of these guys sitting inside each other, right? These open sets sit inside each other. They have limits and such. That's just for the mathematician side of things. All right, so in summary, what we're going to be talking about is local quantum systems. The input, LQS, the input is a bunch of open sets and some sort of a measure or volume on this. It could be a metric. Then the output is we associate to every such open sets an operator algebra. There is a vector. This is the vacuum sector, which is replacing this volume, right? And then there's a Hilbert space. This association, to be physical, should have three properties. This is what we mean by local theory. First, the open sets have inclusion relations. So the open sets have a bunch of relations, inclusions, right? This association of algebras should send inclusion to inclusion. It should respect complement relations. You can have an open set, and you could have the complementary region or the causal complement of it. Then there should be a notion of a complement in an algebra. Roughly speaking, think of it as the commutant, the set of operators in the algebra that commute with it. We'll comment on that. And then it should respect the symmetries of the system. If there is some sort of symmetry that acts on this manifold.
Nima?
Yeah, sorry.
Over here.
So could you tell what are the inclusion relations?
I will discuss. If there's some sort of symmetry relations on the manifold, they should be encoded in terms of symmetry relations on the Hilbert space. So this is going to be the part that the talk is about. All right, so let's discuss this a little bit more.
The role of mu is this d mu, what?
Because I skipped the math part, it's a little bit hard to comment on it, but I'll clarify. I'll try to comment on it as we go along. And if I don't, ask me at the end. Yeah, ask me at the end. All right, so the inclusions. Here's an example of inclusion of regions, open sets for this graph. O1 is inside O2. That means that the algebra that associates to O1 has to be a subalgebra of algebra of O2. Actually, subalgebra doesn't have to be proper subalgebra, so that inside equal. So inclusion goes to inclusion. Good? This is mathematician called isotony. The other one is complement. So if I have so let's start first before talking about complements. Let's talk about the notion of disjoint open sets. If you have two regions, O1 and O2, that are non-intersecting, the intersection is empty, then you would like O1, so you say O1 is inside O2 prime, right? That, in the operator algebra language, should be mapped to algebra of O1 and algebra of O2 commute, right? So this is a weaker notion, but you already see that I've used some notion of complement. Now, a stronger version of this is Hogg's duality. Hogg's duality says complement is literally commutant. The algebra of O1 prime commutant of the algebra of the O1 is equal to the algebra of O1 prime. Complement goes to commutant, right? Okay, so this is all the requirements for a local quantum system. That's Hogg's book. That's the principles of Hogg's book. These are the principles of operator algebras and quantum field, operator algebra get pushed to quantum mechanics, local quantum systems. Yes. Very good. So the status of it is this. In relativistic quantum field theory, for open sets that are topologically trivial, is true. For non-trivial regions, it need not be true, and it's a statement about the symmetries or charges in the system. Yeah. Yes? So that's why I put these in parentheses, right? If you take Riemannian, so just you don't say these are measured open sets, and complement of an open set is complement of an open set, right? So when I talk about Lorentzian, I have to actually be careful. I have to talk about causally complete regions and the causal complement, right? Absolutely. Which part of it is confusing? What is it? I didn't say causal complement. Commutant. So complement of a region is clear, right? So here, this is O. The complement of is O. Think of this as a constant time slice of this. Think of it as phase space.
So you just want to talk about there on state space, not in under time evolution.
Well, if you are talking about the Riemannian metric, I don't know what time evolution is. If you're talking about Lorentzian metric, you have to talk about causally complete, okay, right? So either you go down the route of Riemannian metrics and open sets, and this is a Riemannian metric, the complements go to commutant and all those relations, or you talk about Lorentzian, in which case you have to be careful. So actually, I'm a little bit oversimplifying it because the causal completeness relations are a little bit fancier, so I have to say a lot more math words, but for the purpose of the motivation, it won't matter. Any other questions? All right, so good. So now we come to the symmetries. If your system, your manifold, has a bunch of symmetries, then, which means that these regions, open set, transform under these symmetry transformations. For example, on a lattice, it could be just moving on a graph, it could be moving along these hops, or in Lorentzian spacetime could be translations in time, or null translation, or in space. Then these isometries or symmetries should be covariantly represented on the algebras. If a region O goes to alpha T of O, the algebras should go to the corresponding algebras, and we would like this to be unitarily represented. Now here comes the question that was asked about the measure. So here for symmetry to be so for a second, forget about Hamiltonian. In this talk, every time I say symmetry, what I mean in the classical sense is some transformation of this manifold that keeps the measure invariant. If I have a metric, it should keep the metric invariant, right? So that is the notion of isometry. When I come here, I would require the algebras to transform covariantly, and the transformation leaves the vacuum state invariant. So that's the correspondence, right? So yeah, does that help? But I can get into more details, but. All right, so I already said number 4, that, well, we also would like that the vacuum state is unique. This is the analog of that volume measure, and it's invariant under these symmetries. Otherwise, I wouldn't call them symmetries. Again, you might be familiar more with the language of symmetry as something that can be used with Hamiltonian. This is not the perspective I'm taking here. These are just transformations of the operator algebra that leave your vacuum state or the sector, let me not say GNS, okay, your vacuum state invariant. So the vacuum state is unique. It's invariant under all these symmetries, and there's a distinguished symmetry always in the game that has positive generator. This extra step is, of course, there was a question about Lorentzian and non-Lorentzian manifolds. Here I'm already transitioning to the world of Lorentzian stuff. So I want a positive operator to generate one of my symmetries so that I can talk about dynamics. The distinction between spatial translation and time translations, for me, is just the generator being one of them is positive and the other one is not. Good? All right, so this is going to be the point. Yeah.
Is it important to take EIHT to be unitary? Like, isn't it okay to consider the non-unitary like E to minus B to H?
Sorry, no. So, all right. So based on what I've said, actually unitarity is implied. If you have isometries of, if you have a von Neumann algebra that it has an isometry that leaves a vacuum invariant, it will act unitarily on the GNS Hilbert space. So that's always the case.
Okay, thank you.
It's already implied by all of my requirements. When I say von Neumann, it already guaranteed that. All right. Good. So these 4 principles define for me local quantum theories. And if I take my space to have, for example, to be a manifold, a Lorentzian manifold with a bunch of symmetries, then it would be relativistic quantum field theory. And these are really all the axioms that there is to it to operate the algebraic approach. All right. So now what we did was we encoded geometry inside a quantum system. Can we go in reverse? Can I give you? So the outcome of this is a net of operator algebras, a bunch of inclusions of operator algebras, and a bunch of relations, right? So I now have the notion of commutant, I have the notion of subalgebras, and I have the notion of symmetries. Can I go in reverse? Somebody comes to you and describes an abstract net sequence, some objects with labels O's that are not a priori, you don't know if these are regions of some geometry. Can you reconstruct a geometry? Can you see a geometry in it? Right? So today, this program is actually called non-commutative geometry. In math, I'm a little bit being sloppy here because I had a bunch of slides on that, but let's ignore that. But what I'm saying is that here I'm interested in the case where this algebra is non-commutative and this manifold is Lorentzian. Hence the connection to the emergence of time at the beginning of the talk, okay? So I think this is Is this setup clear? So based on this high-level motivation, I'm going to zoom in and talk about one particular example, which we think is an example of principle that could be generalized. The example is always this, have this picture in mind as we go through. All right, so what does this mean? I have now a net of algebras, a sequence of algebras with these abstract relations, and I want to see a geometry in it. In this net of algebras, I have the notion of inclusion of algebras, subalgebras. I have the notion of commutant, and I have a bunch of unitary isometries. Can I go from these to inclusions of regions, inclusions of these index relations, some notion of a complement, causal complement, and a bunch of transformations of regions? So this index I could be a vertex on a, so one thing that could help is to imagine this index I, or sorry, oops. I'm sorry, this is supposed to be A of O. Change notation. So the algebra of O, the index O is supposed to be down here. So these algebras, you could think of it, if it's hard to imagine, a very abstract thing, think of a graph. Think you're given a graph. That's an easier setup to start. A graph already comes with a bunch of inclusion relations and a notion of a complement, right? So then we're going to focus on these symmetry transformations, right? But if you put the degrees of freedom on edges, actually Hogg's duality might not work, as you might know from lattice discretization of gauge theories. So things are a little bit tricky over there. Yes?
Are you saying that your input is an infinite set of algebras?
Yeah.
Which are like included, and from there, you're trying to get the geometry.
Correct.
And so how do you define the commutants of this algebra now?
Well, the commutant of the algebra is a set of operators in the algebra, in the Hilbert space, B of H, that commutes with it.
But okay, there's also a Hilbert space.
Of course, this is a von Neumann algebra. Yeah.
All right.
Yeah, there's always, these von Neumann algebras always come with the Hilbert space. And yeah, they have a, okay, I don't want to say the fancy words, they have a common cyclic and separating vector, blah, blah, blah. But think of them as living on a Hilbert space. They all live in the same Hilbert space. That's all those words mean for now. Good? All right. Okay, so a motivating example. Imagine, so what we're going to do is we're going to assume we have a 1D lattice, right? And we have a bunch of points. Actually, we have these points sitting like this. I want to see that this system is one-dimensional. That's all I want to do. I have a bunch of, I've associated a bunch of algebras here. I want to abstractly formulate or see that this system is one-dimensional, right? Yeah, ignore these comments. I made a cryptic comment about gauge theories. For now, it doesn't matter. One way to do this is using the notion of half-sided inclusions. Imagine you consider the algebra of all of these guys to the right. I'm going to call that the right algebra, right? As far as I'm concerned, now I suggestively drew these guys as if they're on a 1D lattice. There could be points in the graph, right? Just like scramble them, put them wherever you want. There's no notion of geometry a priori yet. I'm going to define these half-sided inclusions. And now on top of it, I have a unitary flow in my Hilbert space with the following property that's half-sided. When this unitary flow, it's a symmetry, acts on the system, it's for all positive values of n, it sends the algebra to its subalgebras. This is translation in this direction. If I have some sort of an abstract graph and I have such a notion, I'm going to say this is, I see one dimension in it, right? I'm going to declare I've seen one dimension. It doesn't mean that the system could be 10-dimensional. There could be all sorts of directions in that way as well, but I've only identified this. So I say at least I see one dimension in that, right? Is this principle clear? We're going to take this to the continuum limit. So the words that are important is half-sided inclusions and right algebra, right? Because I'm moving to the right as opposed to left. Next, the talk I said is going to be about time. So I'm going to be talking about future algebras and past algebras. That should be clear. It should be an algebra that under time evolution or an evolution with a positive generator will give you some sort of a half-sided inclusions. Yes?
This algebraic notion to some geometry on a line, can you also go to the left and say that the algebra gets bigger? Do you have a unitary doing that?
Yeah. That's right. So I'll comment on that actually. Very, very good point. It took us a long time to realize this, but yes, I'll comment on that. And if it's not satisfactory, I'll comment on the continuum limit. I don't have much to say in this discrete limit, but you'll see that's how we get ADS2 actually. All right, so this is a motivating example. So enough for cartoon picture. Oh, actually I have one more cartoon picture here. If I have something like this and I have P of X, some sort of half-sided translation is this way, another half-sided translation that I identify abstractly, and their generators commute, I call this at least a two-dimensional system. Right? So I see, what have I seen? I've seen the Lie algebra of R2. That's what I've seen. Well, it's discrete, so you know what I mean. Now, I'm going to give you an example from relativistic continuum. If here is like 1 + 1 dimensional quantum field theory, it could be higher dimensional. Yes.
Sorry, could you please clarify the role of the symmetry in there? It looks like you're just using the topology, right?
Well, like it's a unitary transformation that sends my algebras to each other. For all positive values of the transformations, it gives me inclusions. I define what I mean by symmetry. These are unitary transformations that leave my vacuum invariant and they act covariantly on my algebras. On the label.
No, but I meant if you just have the half-sided inclusions, why can't you conclude there's a line? Like, why do you need the unitary transformation to take you from one to the other?
I'm assuming that. I didn't say I need it. My starting point is a net of algebras with symmetries acting on it. Now you might be asking, relax your assumptions. Maybe there's some discussion that we have, but for the purpose of this talk, I'm assuming a net of algebras and a bunch of symmetry transformations on it, right? And then I'm gonna see a geometry in it. A priori, these are unitaries. There need not be a geometry.
Okay, so loosely the geometry will come from the fact that there's a symmetry in it?
Yeah,
or,
so these symmetries become the isometries of the geometry.
Okay, so the one dimension you already have from the topology.
Yeah.
Okay.
Well, I drew it suggestively, right? So this is 1 + 1 dimensional quantum field theory. I can have a setup similar to this. I can have P minus null translation in this direction for these algebras. Actually, think of this picture. I could even be in the regions inside quantum field theory of any space-time with a conformal killing, a Bifurcated killing horizon. So these are the regions. I can talk about null translation in this direction. These are half-sided future algebras. Why future? Because the generator P minus is positive. Then I can have an independent half-sided relation. These are past algebras, right? Because the generator is negative. And because they commute, in this case, they commute, I get basically future algebra, and the fact that they commute gives me you will see, I haven't explained to you guys, but you see the two-dimensional Poincare group, Poincare relations. So this is discrete. I think, let's see, how am I doing in time? Okay, good. So I have I have 12 minutes, so I'm good on time. So far, I motivated it, and I can go on and talk about operator algebraic quantum field theory and all things like that. What I want to do is I want to write down two theorems, right? Based on the intuition that I described to you. These are mathematical theorems. I can provide some intuition regarding the proof. I'm more than happy to discuss you offline about them. The first one is very famous. The second one is less known, but still kind of people who work on this for a living would recognize it. All right, so are there questions from the first half of or 2/3 of the talk, the principle that we're after? What remains of my talk are two examples, two theorems, and the applications to holography. All right, so what are the two theorems? I'm presenting them informally. Actually, I'm not sure if it's informal because the theorems are, well, I haven't written every single word of it, but I'm spelling out every aspect of it. Consider, theorem A, I'm going to call this theorem A. Consider an abstract set net of von Neumann algebras. These A's, they have labels, vacuum, and Hilbert space. And then we have the action of a unitary group, e to the power of IGT. We're going to assume it's a symmetry, meaning that it leaves the vacuum state invariant. I'm going to assume that it has a positive generator. So it has an interpretation in terms of dynamics. And then I'm going to assume half-sided inclusion for a set of algebras. These are the three criteria that I described motivated, right? These are the three really requirements of the theorem. So what does the theorem say based on these? It says that I obtained the Lie algebra of S going to E to S going to A S plus B. It's a non-unimodular Lie algebra. So how does it work? If you have these, so here's the setup. Imagine you take your, oops, sorry, this T should not be there. This should not, so I define A of T to be E to the power of IGT, A E to minus IGT. So these are the translated algebras. The translated algebras will have modular flows based on the requirements, based on the criteria of the theorem. You could prove that the modular flow of these regions and E to the power of IGS satisfy a Lie algebra. This is the Lie algebra spelled out for you explicitly. And it's just what it is the Lie algebra of boost and translations. That's just what it is, right? Dilatation and translations. I should say dilatation and translations, right? So it is, yeah, it's half of PSL2R. PSL2R is a matrix ABCD, right? Here is a setup where this is 0 and this is 1. I get half of PSL2R. So this is theorem 1. This is the very well-known theorem. You could call it half-sided translation theorem. You could call it half-sided modular inclusion theorem. They're equivalent, and it was a very, very surprising result in operator algebras. I would say perhaps after Bisogniano-Wickeman, this was the second biggest surprise or interesting, very, 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 like in the language of Borch's revolutionizing result. All right, is this theorem clear? Yes. No, I did not say the word modular here. All I assumed was that these are von Neumann algebras.
It follows from these three requirements that this inclusion is modular.
No, so yes, it follows. The results follow. The results have a statement about modular flow. Yes, even though in the requirements I didn't write it down. So as it's formulated, you would see that it's more natural to call this a half-sided translation theorem, right? That's also another name for it. They're equivalent.
I see.
Yeah. Usually they're proven as two different results. Turns out that the half-sided translation has a wider range of applicability, but it won't matter for me.
Maybe just a quick clarification on the, a clarifying comment, if you don't mind. The inclusions here are the inclusions of the subalgebras generated by flowing for time t. So each of those is included within the original algebra, and those are the inclusions. And what Nima is saying is that there's this translation theorem that says if you have these inclusions that are generated by positive translations, then they satisfy this nice commutation relation. The converse theorem is that if you just assume you have an inclusion satisfying this nice commutation relation, then you can go backwards and say that one of these generators exists.
Yeah. So, but the way it's really my choice how to present it, and I find this is the least cluttered presentation because otherwise I have to define modular flow and all of that. Just for the purpose of this talk, think of this as some unitary that operator algebras define for you, and they guarantee that they satisfy this quote unquote half of PSL2R for you. Good? All right. So I have 6 minutes left. I can spend the other 6 minutes on theorem 2. Theorem B, sorry. So here's theorem B. Theorem B, the goal of it is to get the full PSL2R, right? Again, like the last theorem, I can present it in many, many different ways. The simplest way, which I'm going to present here, there's a little caveat. We know a more general version of this, but it's a little bit uglier to present in a short amount of time, so I'm just going to go with this version. Here's theorem B. It says, consider the setup of theorem A. So these half-sided inclusion, positive operator, future algebras, right? Future algebras, keep that in mind. Consider future algebras. So this is what we had before. AT is inside A for all positive A. Now, here somebody asked about Raghu asked about, what about the other side? Here, I have AT inside A, you could ask about the other side or the relative commutant, which is part of AT operators in A that commute with AT. This is the closest notion to the other part, right? This is called a relative commutant. In this picture, you would, in quantum field theory, you would think of this as operators localized here on this null region, null segment, right? So is the relative commutant clear? Relative commutant of an inclusion, B inside A, or sorry, that's a poor name. AT inside A is the set of operators in A that commute with AT. That's what the relative commutant is. All I need to say is that this B, this relative commutant, is cyclic. Meaning that if you act with the operators here on your vacuum, it gets you everywhere in the Hilbert space. So it satisfies the criteria of Riesz-Leiter theorem. Remember that a priori, Riesz-Leiter theorem already had geometry included in it, right? Riesz-Leiter said to every open, the algebra of every open set, if you act on the vacuum, it gets you everywhere. In my definitions, this B has an algebraic definition. I'm not associating any space-time region to it a priori. If I know it satisfies cyclicity, which is like a Riesz-Leiter, then I instantly get, so these are the criteria of the theorem, then I instantly get that the modular flow of A, modular flow of A1, this is translation by 1, and modular flow of B, they generate a PSL2R group. So there is a two-dimensional conformal group right away. I can even comment on the proof and what is going on. The idea is very simple. The idea is, let me go back. When you have this setup, the fact that you start with theorem A, it means that you have half of this PSL2R. If the relative commutant is non-trivial, then you can easily see that translation in the other direction will give you a notion, actually modular translation in the other direction will give you a notion of a past modular algebras. I didn't define that, I understand, but if that's already, to some of you guys, it might be familiar. That gives you something which is another copy of this group that I'm going to suggestively write like this. You know that if you have two sets of translations, all you need to get the PSL2R, you have two sets of this AT plus B, all you need to get the PSL2R is inversion, right? Translation, dilatation, inversion gets you the full PSL2R. Because special conformal transformation is translation, inversion, inversion, translation, inversion. So what is this inversion action? It's just swapping B for A of T. Swapping the two ingredients of the relative commutant, of the algebra. That is where you get the inversion from. And you get the full PSL2R group. All right? So that is theorem B. Any questions about theorem B? In the remaining 2 minutes, I'm going to go through applications in holography. Any questions? Sorry?
Maybe not exactly about theorem B, but something about the symmetries. Like, can I ask?
Yeah.
So, so every time you have some algebra and some symmetries, and then so can I make a statement that every Cartan subalgebra or something corresponds to a horizon? Or is it like every bounded Cartan?
Let me not go there. These theorems, the generalizations, some generalizations exist, but let's talk offline about this. Sure. There are lots of subtleties. I mean, it's an art to abstract out these theorems, and these people who have proven theorems of this nature have worked for decades. All right. So what the content of the paper, just 1 second. The content of the paper we've written is a generalization of this is a generalization of this theorem B that I will not present, but I'll tell about the application of it. Good. If you allow me to, I have 2 minutes, let me just finish this and then. So applications, I'm going to list only 2 applications, all right? So what are these applications in holography? I have a boundary theory. It's quantum mechanics. It's 0 + 1 dimensional quantum system. Think of it as generalized free fields, right? But it's some abstract quantum mechanical system, and I want to see that this quantum mechanical system is dual to some eternal black hole. That's what I want to do, right? So first, I notice that, okay, I'm gonna switch here. Now I'm gonna identify I'm gonna assume I have algebras in time. As we learned from Liu and Luthauser, some systems at large allow you for such setups, but these are abstract things, right? So T abstractly is just a label for my net of algebras, right? I'm gonna label these guys here. I have a time future algebra of generous free fields in this setup. I have the spectral density. I'm in a KMS state, finite temperature state, so all I need to define everything is just spectral density, right? So I'm gonna take the spectral density that corresponds to, that we know from holography, corresponds to eternal black holes, right? It's just some choice of a spectral density. It defines for you, oops, sorry, just 1 minute. It defines for you some quantum system, right? Now, by applying theorem B, you recover the action of a PSL2R on the horizon on H plus, and an action of PSL2R on H minus. These are the conformal symmetries on the horizons of eternal black holes. So this is one theorem we could prove in the bulk, right? Then the other theorem that you could prove is the case of ADS2. Imagine you have this algebra. So you might be thinking that, oh, this PSL2R you're acts like a conformal transformation on this this null hypersurface in the bulk. Sometimes that's the case, as I told you, but sometimes it acts like ADS2. Example, take for example Poincare patch of ADS2. You have some quantum system on the boundary. This is the spectral density of it. You could prove that from theorem B that there is a PSL2R that acts everywhere and it's nothing but point by point ADS2 symmetry in the bulk. Now, if you have a setup which is like a ADS2 Rindler, you have to generalize these theorems because what you have is not literally PSL2R. You have the action of the universal cover of PSL2R. So you have to generalize this theorem to allow for that, and that corresponds to non-integer values of delta. Thank you very much.
Thank you, Nima. We have time for 1 or 2 quick questions.
I have a naive question about your principle. So you said we need a unique vacuum for defining von Neumann algebra.
Yeah.
Then what happens to asymptotically flat space when the vacuum are like degenerate level by the supertransmission sector?
Sorry, asymptotic flat space is not a problem. What was the question?
You said that we need a unique vacuum for defining a von Neumann algebra.
I need what?
Unique, like one single unique vacuum.
Oh, a unique vacuum.
Yeah, and now in asymptotically flat space you have this degenerate vacuum level.
Let's say I'm only talking about theories with a mass gap. In asymptotic flat space, I'll restrict myself to that. If I'm talking about mass test series, I'll just embed the Minkowski thing inside the Lorentzian cylinder and talk about CFTs. Yeah.
Okay. So for those things, it's not defined.
I do not have any comments to make about massless modes that are like QED or something like that.
Okay.
Yeah.
Thanks.
Any further?
Can you go to this slide where you drew the relative commutant of the future algebra?
Yep.
Yeah. So theorem B, which is I think Wiesbrock's SL2R theorem, it requires this setting where you have a relative commutant of this shifted algebra within the sort of full exterior, black hole exterior, which I think requires you to have operators that are localized to the horizon. And I'm a little worried about the existence of such things outside of free field theory. So do you have any comments on that?
Very good. Yeah. You should be worried. You should be worried. And indeed, what you're asking is that, well, you should be worried about the same question in the context of quantum field theory on this background. You should be worried. So whatever takes care of that takes care of this. The actual PSL2R is there. It might, if the theory is such that these null intervals algebras are trivial, you're talking about a triviality. However, there are lots of interesting theories where we think that these translations along the horizons actually act on algebras, and you could construct such examples. In those examples, you could see explicitly that this action is there. Otherwise, you could say this is just a triviality acting on the trivial Hilbert space. The theorem still goes through in a trivial sense.
Yeah, so, I also want to ask the same kind of thing. Like the B, can you shrink that period?
So, okay, the reason I said that if this is cyclic, that was an assumption, is that this is, I'm assuming sometimes ends up being a zero volume, zero measure set. If this was finite volume, I would have expected to always be cyclic, right? So a priori, because I don't have a geometry, right? This is an assumption, and it's a loaded assumption, it's deep enough to give you PSL2R.
So if I take this to the flat space, like Minkowskian, so
yeah.
I can apply there also, right?
Yeah.
So is it equivalent to saying that that I0?
The criteria that I've listed here will not survive in flat space. The flat space algebras will not satisfy these. There's a modified version of this that they will satisfy, and that version will give you actually the SO2 comma 1, SOD comma 1, the Lorentz group. The Poincare group actually gives you the full thing. Yeah, there's a version of it adjusted for that.
How different is this from the Riech-Leiter? What extra is there?
No, it's not Riech-Leiter at all. So Riech-Leiter says, assume a local quantum field theory. The action of open sets on the vacuum gets you everywhere. Here, I'm deriving a local field theory.
Thanks.
One last question.
Yeah, hi, Nima.
Yes.
So it's a very sort of pedestrian type of question for what you have said, but you know, I mean, we know what quantum field theories are. I mean, and so I'm really would like to ask you whether you have a constructive algorithm or proof for how to compute these operators, delta, H, and all that you talked about. Or what are your assumptions? You're just stating that it exists.
Right,
what does it mean?
So very good. That's indeed a very important question. As physicists, we work with examples and we could get lost in abstractions. All the examples we have at the moment are of the nature of generalized free fields. So in generalized free fields, we can be explicit, and we are trying to be explicit. We could calculate some of these modular flows. We could see some of these explicitly. Unfortunately, I don't have a more detailed answer for you. So generalized free fields is the only set that we have only been able to work with so far. And even in that case, you'll be surprised how hard sometimes these calculations are. But yeah, ideally, I would like to move away from that, and we're not there yet, unfortunately.
Okay, let's thank Nima again.